Hi class, we are going over test 2 review. Now I had a number of technical difficulties while recording this, so what I have wound up doing is I have the solutions written and we will go over them in this video rather than me writing in real time. Okay, so the first one, we're given a matrix A, and the nice thing is we are also given the reduced row echelon form. This matrix is 4 by 5, and instead of having to do a number of elementary row operations, we can refer to this. Now, we can work on, or we can answer C first, because let's look at the reduced row echelon form right here. We see 1, 2, 3 leading ones. This says that the rank of the matrix is 3, and immediately this says that the dimension of the image is 3. It's the dimension of, well, the dimension of the image is the same as the rank. And then we also know that the dimension of the kernel will be the number of columns minus the rank. So that would be 5 minus 3, which is 2. You could also get the dimension of the kernel by counting the number of free variables. You see we have a free variable corresponding to x2. We have a free variable corresponding to x5. This will give us 2 elements and a basis for the kernel, or the dimension will be 2. Okay, well now let's begin. To find a basis for the kernel, we start off with these 2 free variables. I just said x2 was t, x5 was t, and then we have this 1, 2, 3 equations, and they are here, 1, 2, 3. These allow us to solve x1, x3, and x4 in terms of t and s. And this first one, for example, x1 is minus 3t minus 7s, x3 is minus 9s, and x4 is positive 6s, just like this. So we get this one vector, which is a general vector in the kernel of this matrix, where t and s can be any real numbers. So then you break it into this sum. We have t times this plus s times this, just as we have practiced, right? And then this is one element in a basis, and this is a second element in a basis, or in the basis, I should say, for the kernel. And so it's written here. The kernel of A is the span of these 2 vectors. Now, you don't have to write it's the span. You could literally just list this vector and list this vector. That's your basis. So this has answered A. But now 1B is in effect, it's simpler than 1A because we don't even have to write anything. Once we see the reduced row echelon form for A, well, you have to be careful. Do not just pick out the columns in this where you have leading ones, because this is not correct. But you see we have leading ones in column 1, 3, and 4. So we pull off column 1, 3, and 4 in the original matrix A. That should be what I have written down. Okay, looks good. This is column 1, column 3, and column 4. These will form a basis for the image. They are the columns in A that correspond to where you have the leading ones in the reduced row echelon form for A. Okay, so this finishes number 1. Now let's move to number 2. We have 2 questions, and it continues on the next page. The first one is this a basis for W? We're given 3 vectors in R3, and W is the span of these 3 vectors. Well, we already know that 3 vectors span. That's by definition. So the only other thing we need to check is, are these 3 vectors independent? Because we know a basis for a subspace must be, number 1, independent, and number 2, must span. So spanning sort of is given to us here. Now, this is not the only way to check independence. Let me tell you what I did. I put B1, B2, B3 in columns of a matrix. And then if this matrix is rank 3, the number of columns, this says the vectors are linearly independent. If the rank is less than the number of columns, this says the vectors are linearly dependent. And I did it this way for this choice of B1, B2, B3, namely because in one step, I get myself to not reduced row echelon form, but row echelon form, which is enough to tell me the rank. So this was one step. I took minus row 1, added it to row 2, and I am here, row echelon form. Immediately, I see the rank of this matrix is 3, which is the number of columns. This says these 3 vectors are independent. And like I said, we're already told they span. So we have a basis. Okay. In fact, W is R3. Because look, we have 3 vectors in R3 that span W. So W is a 3-dimensional subspace of R3. That means you are R3. The only n-dimensional subspace of Rn is Rn itself. Okay, great. Well, now let's move on. We need to use, this is 5.1 is part B. We need to use Gram-Schmidt to find an orthonormal basis for W. Really, it's an orthonormal basis for R3, but it's using these 3. Okay, the first step is always the easiest. U1, so I'm going to take B1, B2, B3 and construct U1, U2, and U3, and these will be my orthonormal basis, okay? The first step, U1, you just take the first element and divide by its length. That's always the easiest one because you don't have to do any projections. You just normalize. It's not that hard to see that for this vector, the length is square root of 2. And so this is U1, okay? Then now we start the process of Gram-Schmidt. The first thing we do is we create a vector that is perpendicular to, well, what's come before it. In this case, it's just U1. So we create a vector that's perpendicular to U1. And then we normalize it here. So the 2 steps, and then we do the same thing to get U3. And this is, you take B2 minus the projection. Okay. U1 is unit, and so the projection comes into this formula. We have B2 minus the projection of B2 onto the line spanned by U1, or equivalently onto the line spanned by B1, same line. And so here you see my work to calculate U1 dot B2. It's 4 over square root of 2. And then I just take difference. I take B2 minus this constant times U1. I get this vector 0, 3, 0, which is not unit. In fact, it has length 3. Okay, but you can check. Look, this vector and U1 are perpendicular. They dot product to 0. Then I take I define U2 to be this vector divided by 3, its length, and I get this. This is this E2, the standard vector, okay? So far, we have 2 vectors in our orthonormal basis. We have U1, we have U2. We need to construct U3 using B3. So let's move forward. You see, I recopied U1, U2, and here is B3, okay? Now this second step, or third step, I guess, in the Gram-Schmidt, this time we're still creating this vector perpendicular. It's going to be perpendicular to both of these. In fact, it's going to be perpendicular to the subspace spanned by U1 and U2. And the way we do this is this part, we take B3 minus this part, which this part, wait, let me let the first part erase. Okay, now, this part is negative the projection. So you project B3 onto the subspace, what's going to be a plane, spanned by U1 and U2. Then you take this B3 minus the projection. And this was this component of B3 that is orthogonal to this plane spanned by U1 and U2, okay? Then we normalize, divide by its length, and we get a unit vector. And so this is what I did here. Here's the formula for projection here. Well, I've distributed my minus sign, but we have B3 minus the projection. Here's B3 from here. And then over here, I show the work calculating these two dot products, U1.B3, U2.B3, which come in front of these vectors. And then you take this, minus this, although you can go component-wise. For example, 2 minus, this is 6 over 2, 2 minus 3 minus 1, right? And you could do that for each component, and you realize that this component of B3 that is orthogonal to the plane is this vector, okay? Then the final step is you divide by its length. And again, if you look at this vector, you see the length is square root of 2. So we take this divided by square root of 2, and we get this vector here, okay? And the final step is just to list the answer. We have found an orthonormal basis. It is right here. This was U1, U2, U3, and it's not a bad idea to check that they are all perpendicular to each other, and each vector listed here is unit. So this says it is orthonormal. Okay, let's see. Now we move on to number 3. We want to find the angle between these two vectors, V and W and A. And B is a separate problem. Again, I've labeled it V and W, although it's a different V and W. And we want to find the value K such that those two vectors are perpendicular. Well, this uses this sort of geometric interpretation of the dot product, that the angle between two vectors, V and W, you take their dot product, the angle between two non-zero vectors, V and W, you take their dot product and then divide by, here, the product of the two lengths. And so this is what I need to compute in this problem, and then I can use the cosine inverse or arc cosine function. If I take V dot W, this vector dot this one, you see I get 1 minus 1 plus 1 plus 1. I get 2. Now, V and W have the same length. It's both the square root of 4 or 2. So the cosine of theta is a half. Okay, well, this says that theta, well, we always take it to be between, let's see, between 0 and pi, or 0 and 180 if you're a degrees kind of person. It says the cosine of, or the theta, excuse me, is pi over 3. Okay, this is the angle between these two vectors. Now, if I move on to B, and A and B, these could be maybe like in the first week of Calc 3, for example, but they also come up for us in section 5.1. Two vectors are perpendicular provided their dot product is 0. So this is what I need. V dot W is 0. And so for this V and this W, I just compute. I get 2 plus 3K minus 5, which is 3K minus 3. And we see that the two vectors are perpendicular provided K equals 3. Okay, now we move on. Okay, this is another projection problem. We have several of these in this. In part, this is the newest material. 5.1 and 5.2 all use this. V is a subspace of R4 spanned by these two vectors. Then we just check. Well, of course, here, take their dot product, you get 0. They're orthogonal. Neither vector is unit, so they are not orthonormal. That's why orthogonal is the best choice. Then I want to, this is kind of like we did in the last problem. I want to decompose this vector into this part, which is the projection onto V, this two-dimensional subspace in R4, and this part, which is the component of y that is orthogonal to v. Okay, so in fact, if we even look ahead, and I will go over how to do part C more than one way, but an observation that we can make is that this that we will find will be in this subspace because it will be orthogonal to V, and that means you're in V perp. Okay. Well, I like to use this projection formula when I have unit vectors just because it's a little bit easier. So the first thing I do is I take this V1, V2, and I normalize them. Now U1 and U2 are units, and they form a basis for V. Okay, so U1, U2 are unit vectors that form a basis for the same subspace V. Now let's see what's happening. Okay. The projection formula, when you have unit vectors, well, we saw it a little bit last time in the Gram-Schmidt. We just take, I'm not sure why I wrote it y dot u1 here and u1 dot y here. It's the same thing. You can dot product in either order, but you just take u1 dot y, that's the coefficient, times u1, and then plus u2 dot y, that's the coefficient, times u2. This is the projection. This formula is the correct one when you use an orthonormal basis for projection onto a subspace. And then up here, you see my work for calculating u1 dot y and u2 dot y. I just multiply each component and add. Okay, so I get 1/3 and 11/3 for those two. And then I just put them here. This component, or this number dot product times u1 plus this dot product times u2. And okay, well, these fractions aren't the prettiest. It's okay. This is what it is. So this vector here is the projection onto the subspace V. And then this component of y, if I move up, this component of y that is orthogonal to V, we take y minus the projection. Y minus the projection, we get this. Now, it's good to check this. If I was doing an exam and I was computing something like this, I would check just to make sure, because it's so easy to make a mistake. I do it all the time. In fact, that's life. And I'm sure you do too. As you're working through problems, sometimes you make a mistake, then you find it, fix it. But it would be really nice to find and fix the ones that you submit for an exam. So if I got to here, I would take this vector, which should be perpendicular to both u1 and u2, and just dot product this and dot product this, and you will get 0. Or you made a mistake, and then you go back and you find maybe it's a minus sign you missed, something like this. Okay, but this y perp, well, the component of y orthogonal to V is calculated here. Okay, now we need to find part C, a basis for the orthogonal complement of V, which is V perp. Okay, well, let me talk about way number 2 first. Just because I'm on that, so I'm going to go back and discuss way number 1. But way number 2 follows from part B much more naturally. Okay, so what do we know? We know that V is a subspace of R4. We know the dimension of V is 2 because it's spanned by 2 orthogonal vectors, and orthogonal vectors are independent. So the dimension, those are a basis, right? Now this says that this V perp, its dimension will be 4 minus 2, which is 2, okay? This is what we get by this sort of dimension counting. And we found this component of y that is orthogonal to V, as I mentioned, it is in V perp. So we've already found one non-zero vector in V perp. So to get a basis using the work we've already done, all we need to do is find one more vector in V perp that's not a multiple of y. And then I recopied what V is, the span of these two, and you just look. Well, this vector, E4, this standard vector, is very clearly in V perp. Because you dot product it with this basis element, you get 0. Dot product with this basis element, you get 0. And that means if you dot product with any linear combination of those two, which is any vector in V, you will get 0. So this is a second vector just by looking at this basis for V, we realize this vector is in V perp. Okay, so then now we have a basis for V perp. We were looking for two linearly independent things in V perp, and I have given you two linearly independent things in V perp. This means we have a basis. Okay, well, the question might become, or might be, what if I didn't have zeros here? It's not so easy to always spot an element that's perpendicular to a collection of vectors. So this is why I said this was way 2. And way 1 is the way I would go about it. Let's go back. Way 1 is the way I would go about this if I hadn't already done the work of part A and part B, okay, where I was just handed this. And then the vectors that were in a basis for V just had zeros in one place, and I could easily find a second vector. And this way came up in homework, and this way will work always. Just make a matrix such that V perp is the kernel of that matrix. And how do you do it? Well, let's go back. My original vectors are this one and this one. I can put those, can we see? I hope so. This one and this one, I can put those in rows of a matrix. And then anytime you take one of those dotted with the column, this dotted with that, well, that's saying that any vector in the kernel of this matrix will be in V perp. That's what my observation is here. And you could put them in any order. You might naturally put this one in row 1 and this one in row 2, but just because this one has a 1 in the first entry, I put that in row 1. So now I already have my leading 1 in the 1, 1 spot of this matrix. Okay, so this was, here was one of my vectors, here was the other, and then we put something here like I was saying, you take this dot this, you get 0. That's precisely saying being in the kernel of this matrix is precisely being in V perp. Okay, I said it once, I said it again. Now let's just find the kernel of this matrix. This comes from row operations, so I perform row operations here. I'm not going to talk through them. We've done this a number of times. You can read them. But I get myself to here, which is reduced row echelon form. And then I'm just finding the kernel of a matrix, just as I did in number 1, for example. We see x3 and x4 are free. I called x4t. I called x3s. And then the first and second equations say that x1 is minus x, as x2 is negative 1/2 s. And so just like we did in number 1, the very first problem on this review, this is a general element in the kernel of this matrix. And I can write it as a sum of s times this vector plus t times this vector. Okay? And then finally we get here, we pull those two vectors off for a basis. So this way, way 1, which I actually went over second, is a way that always works. If you have a basis for V, and you want to find a basis for V perp, and we practice this in the lecture, you just put the vectors of V as rows in a matrix and find the kernel of the matrix. This will work even if you can't eyeball anything that's in V perp, as I could in way number 2. Okay? So I like both those ways, but I also, well, okay, that's why I list them in the solutions. Wanted to go over them both. Now we have QR factorization. Again, projections, projections, projections. Well, it's the most recent topic, and I wanted people to practice it a lot. Now, if you watched all the way to the end of the 5-2 video, there was a point where I said if you want to stop watching now, you can, and then I continued. You can find this R by, once you have Q, Q will be the orthogonal matrix. Q is the columns. The columns of Q are just the vectors that you get through Gram-Schmidt on the columns of A. Okay, so in effect, it's nothing different than we've already done, even in this review. But the question is always then, how do you find R, which is this upper triangular matrix with positive entries along the diagonal? So you can either memorize what goes into the entries and fill in R as you go. That's one way. And I think I did an example both ways in the lecture, or you can multiply. Well, you're given A, you calculate in this process Q, just take Q transpose times A, and this is another way to get R. If you didn't watch that far in the video, you can watch it and see, okay, how I discuss this. Okay, so let's talk about this here. This is V1 and V2, and I'm going to be creating a U1 and U2. I think this is one of the unassigned exercises from the text. I just pulled off to get another example of QR factorization. First, we take this. Well, I calculate the length, take the vector, divide by the length. Now I have a unit vector in R4, and it's this. Okay, so far so good. But then, just as we practiced in one of these previous problems, I take this. This will be the component of V2 that is orthogonal to the line spanned by V1. And then I take this, divide by its length, and then well, now I have two orthonormal vectors. I put those in columns to get my matrix Q. Okay, and this is the formula as we have discussed. I have a unit vector. I take V2 minus this dot product times U1. Here is my work, this dot product. Well, we get 7, okay? V2 dot U1 is 7. So then I have V2 minus 7 U1, and we get this vector. Okay, it's not unit, not yet. Then we normalize. Okay, so move to the next page. U2 is this vector, the component of V2, orthogonal to the line, divided by its length. I recopied this, calculate its length. We also get 7. Here is U2. Just take this vector, divide by 7. And finally, well, in terms of finding Q, we just put U1, U2 as my two columns. This is the matrix Q. But here's where I mentioned about you have two different ways to find R. If you want to memorize what the entries go, this is the length of V1. This is the length of, well, this component of V2 that is orthogonal to the line. And then this dot product, U1 dot V2. This would be what you can put in your R here. All of these were 7, okay? Or, and this is not that too bad to remember when you're just doing a 2 by 2. But if you had, say, a 3 by 3, then sometimes it's hard to remember to fill it in. Or you can just take this Q, take its transpose, which was interchange rows and columns, multiply in this order by A, and you will also get this. It's really your choice how you do it. Like I said at the end of the video, this is fine to remember for 2 by 2, but for 3 by 3, I already forget how it goes. So I always just remember this. It's easier, and all you're doing is you just interchange rows and columns, and then you multiply, and then you have the matrix R. But how you find R is entirely up to you. One of these two, okay. Then this is the R. So this is the Q, this is the R, QR factorization. Okay, whew. 6. Let's see how much we still have. We have, we're on the second page, which means, let's see, we're done with the projection part. A lot of projections, but we have a lot to practice. 5.1 and 5.2 is a lot of projections. Okay. This goes back to chapter 3, I think all of number 6. Justify your answers. And part A says, is this a basis for R3? Well, I said yes, and then I start justifying it. We have 3 elements, okay? And R3 is 3-dimensional. So anytime we have 3 elements that spans a 3-dimensional subspace or vector space, it's a basis. Equivalently or similarly, anytime we have 3 elements that are literally independent in a 3-dimensional subspace or 3-dimensional vector space, they are a basis. So when you have the right number, this is 3-dimensional, this is 3 of them. When you have the right number, you only have to check either linearly independent or spans, and then you will know you have a basis. Now, to show linear independence, we can, and I will on maybe on this one, the one below, part B, you can just put those vectors in the columns of a matrix and then say what the rank is. And that's justification. If the matrix has rank 3, then you know, well, 3 by 3, or I should just say 3 columns has rank 3, then you know those 3 columns are independent. But you could also, this, I just chose to do a different way. This is going back to this linear relation. So if you have sub C1 times this vector plus C2 times this vector plus C3 times this vector equals 0, it must be the case. C1 is 0, C2 is 0, and C3 is 0. And this is another way to show the vectors are linearly independent. And this way, well, I mentioned in the video, a lot of times if you're working abstractly, which this isn't that abstract, we have actual numbers in our vectors, but if you're working abstractly, this way is frequently the easiest to show a collection is independent. But here, if I had this, well, it really comes, it has 1, 2, 3 equations coming from this. And the third equation, already looking at zeros, it says 5C2 is 0. We get C2 is 0. Once we have this equation would say 1.1 C1 is 0. And then we have C1 is 0. Once we have C1 and C2 are 0, this top equation just says square root 3 times C3 is 0, and we get, in fact, all 3 coefficients were 0, which says these 3 vectors are independent, meaning, well, since we have the right number as the dimension, they form a basis for R3. Okay. Now, I move to the next page to discuss I and II, but I and I, but two I's I put on the bottom here. There's no way this set is a basis for R4. We have 3 elements in R4. They're never going to span. Okay, the biggest dimension they can span is a 3-dimensional subspace, and that happens if they're independent, which they will be. That's on the next page. But you never will have 3 vectors in R4 that form a basis for R4. You don't have enough. So the answer to 2 I's is no. Okay, but then here, and this is one, again, I could have said C1 times this vector plus C2 times this vector plus C3 times this vector is 0. Show C1, C2, C3 are 0. That would probably be just as nice or just as easy as a observation, but you can also just look at rank. I purposefully tried to justify more than one way in these different examples. This rank is 3 because we have 1, 2, 3 linearly independent columns. You could also get yourself to row echelon form or even reduce row echelon form in not that many steps, but the rank is definitely 3. which says these three vectors are independent. And then this asked if these three vectors were a basis for the subspace they span. And I just said yes, because they're independent. And then by what it's asking us, they are already a spanning set. Okay, we have one more, and this is 3.1. This is the very start of the material, I think. 3.1 is, 3.2, excuse me. But this is chapter 3, subspaces. Which are subspaces? And justify. Well, the first one clearly is all linear combinations of two vectors. This is, you're taking the span of two vectors, and everything that's the span of some collection of vectors is a subspace, okay? In fact, these two vectors we see are linearly independent, so this vector and this vector form a basis for the subspace they span. But we're not asked all of that. Yes, it's a subspace. Now this one, all vectors in R3 that satisfy, you add up the coordinates and you get 0. This is a subspace. The easiest way to justify this, at least in my opinion, is to observe it's the kernel of this matrix, right? If you have a x1, x2, x3 here, then you multiply, you get exactly this. So all vectors in R3 satisfying this equation is the kernel of this matrix. And we know kernels of matrices are subspaces. So that's a justification on this. On 7C, the answer is no. I would be really hesitant anytime I saw a less than or equal to and having to do with a subspace. That's just my intuition, but how do I justify this? Well, we know about subspaces. Okay, if we go back to what is a subspace, you have two vectors in the subspace. The atom has got to be in the subspace. Then you have a vector in the subspace. You take some multiple, has to be in the subspace. And then the third thing is that 0 must be in the subspace. So here's a vector that is without a doubt in this set, because -1 is less than or equal to 0 is less than or equal to 1. But here is a multiple of it. -2 times this vector is this vector, 2, 0, -2. This is not in this set because, well, 2 is bigger than 0, is bigger than -2. Okay, not in the set. So in fact, we do not have this was the terminology closed under scalar multiplication. This set is not, so it's not a subspace. Okay, now all we have is the true false. And just like with the last review, I talk about why, because that's an important part. You know you will have true false, and you don't have to justify it on the exam, but you certainly have to understand why you're choosing them, at least to increase your likelihood of getting them right. Okay, so here, there is a 4x4 matrix A such that the kernel and the image are equal. No, the dimensions wouldn't work out. So here, if you had the kernel of some matrix equal to the image of the same matrix, well, the rank of the matrix is the dimension of the image. The nullity of the matrix is the dimension of the kernel. So these two numbers must be equal. We have a theorem, rank nullity theorem, that says the rank of A plus the nullity of A equals the number of columns. This has 3 columns, but with these two equal, this says that 2 times the rank must be equal to the number of columns, 3. Well, this is not possible because the rank is an integer, right? You can't have the rank of a matrix be 3/2. So that says that this is false. Okay, B. B is true. This says there exists a 4x4 matrix A such that the dimension of the kernel equals the dimension of the image. Well, I just illustrated one. This is a there exists. So it's true because I hand you one. Here's a matrix A. In fact, it's already in reduced row echelon form. We see the rank is A. That means the dimension of the image is A. The dimension of the rank is 2. Excuse me. Okay, you can tell we're getting near the end of the review. The rank is 2. That means the dimension of the image is 2. Got to be a number. Sorry about that. Well, the dimension of the kernel will be 4 minus the rank. So we also get 2. Okay, so this calculation came from rank validity. Really? So here we have the dimension of the image and the dimension of the kernel are both 2, and they are equal. Okay, so far so good. Yeah, okay, C is false. It doesn't say anything about the vectors being independent. So if you knew these vectors were independent, then without a doubt, this would be the dimension. But you take any 3 vectors, and that's not the case. In particular, here's a counterexample. R2, which we know has dimension 2, is the span of these 1, 2, 3 vectors. I could have put R2 as the span of 15 vectors if I wanted to. It doesn't mean the dimension is 15, okay? Wouldn't be 15 independent vectors. There's only a maximum of 2 independent vectors that you can find in R2, okay? That's the number of things in a basis. Okay, I think we're okay. Hope so. Now, let's see. Okay, very nice. We start off by saying B1, B2, B3 is a basis. So immediately we know the dimension. This is telling us the dimension of V is 3. Oh, I wrote it right here. So then if you have a collection of 3 vectors that spans a 3-dimensional subspace, immediately you know, and I mentioned this in a previous example, immediately know that is a basis. So the answer is true. E is false. Orthonormal is the part that's false. These 3 vectors are all perpendicular. They are orthogonal. You take this dot this, or this dot this, or this dot this, you get 0, but the lengths are wrong. This vector is unit. This one's not unit. This one's not unit. So it's not an orthonormal basis for Rn. Okay. If A is n by n, then the dimension of the image is 0. It isn't, oh, I missed a word. Invertible. Yeah, doesn't work like this. Invertible matrices, their image is all of Rn, which has dimension n. So this is false. If this said, if A is n by n invertible, then the dimension of the kernel of A is 0, that would be good, but not as it's written, not with the image. And this one's similar. A is n by n invertible. The kernel of A, this is to the 10, this is the power of the matrix, is the 0 subspace. Yes, this is true because we had a theorem. If A is invertible and B is invertible, A times B is invertible, and there's a formula for the inverse for A times B. Well, that's 2 matrices, but 10 would still hold. So here, if A is invertible, multiplying A by itself, A times, still invertible. A to the 10th is invertible. Okay, which says, and this is a little bit like we were discussing here, that the kernel is 0. Okay. 2 more. H. A is 8 by 9. This is the number of columns. It has rank 8. Says then the dimension of the kernel is 0. No. Ring validity, you work on columns. So ring validity, the dimension of the kernel is the number of columns minus the rank, which is 1, not equal to 0. And then finally, this is false. This is something that holds for orthogonal, perpendicular vectors. In fact, I think I used that in 5.3, which is something that you should, I mentioned it in 5.1, and then I use it in 5.3. It's something that you will have watched, but it has to do with lengths. Okay, fine. What we really need to do, so we think the answer is false, or maybe think it's false because we remember it only holds for perpendicular vectors. But if you want justification, here are two vectors, 1, 1, and 1, 0, and they are definitely not perpendicular. Their dot product is 1, not 0. I add them together, I get 2, 1, and then I just start computing. This length squared is 2. This length squared is 1. This length squared is 4 plus 1, 5. But 5 is not equal to 2 plus 1. And so you see this is false. Okay, this is the end. I will upload the solution and this video to Canvas. Thank you very much.